Okay, guys, we are just going to continue with going through last year's, and I keep saying last year's, but this just happened in May. So the free response from last May. Um, so again, this isn't really me trying to teach you all these concepts. I am going to, cover the answers and hopefully you understand some of it and you probably don't understand a lot of it based on what we were able to cover last year and the year before in Chemistry 1. So this is just me. I'm trying to show you how, getting familiar with the structure of the test, what it looks like, but also just seeing how the test kind of marries up to our visible learning document. And, when I give you this visible learning document at the beginning of the year and it has, you know, all of this stuff in it, this is what is covered in AP Chemistry or what needs to be covered in AP Chemistry. And what I want you to see is every question that is on the AP exam and every question that would be on your final exam, every question that's on your unit tests and that kind of thing, there is a visible learning objective or multiple visible learning objectives that each question is asking about. And if you understand the visible learning document, by the time we get to next May, and it's time to take the AP exam, and it's time to take the final exam, if you get most of the stuff on this document, on the visible learning document, if you're like, oh, I can do that, I know how to do that, I recognize this, and it doesn't have to be 100%, but it's got to be a good amount. You can easily, and again, if it's not easy to get to that point, but if you are at that point where you're like, oh, I look at this document and I understand everything's on there, then you should have no issues getting a very good score on the AP exam. So I just kind of want to show you that, like, here's the question, where was it in the visible learning document? Oh, there it is, that kind of thing. So that's all this these videos, this group of videos that I'm posting is just trying to get you to understand. So let's go to question 2. Okay, in question 2, if we look at the visible learning objectives for question 2 has A, B, C, I, C, I, D, E, F, G, right? So that's 1, 2, 3, 4, 5, 6, 7, 8. 8 different questions, okay, in question 2. And remember, if you're looking at the way the exam's structured, question 1 is worth a total of 10 points. Question 2 is worth a total of 10 points. And then when we get to question 3, that's a total of 10 points. So there's 10 points embedded. So obviously 2 of these are going to be scored by 2 points, right? You're going to need to get 2 points out of 2 of these. But I'm not sure which one. I have a good idea of what I think might be the 2-point questions and which are the 1-point questions, but they haven't, thrown out the official scoring guide for this test. So it's just me, guessing. All right. But I can show you the visible learning objectives that it covers. All right. So this one starts out with oxidation reduction, and then it goes into, where am I going here? Then it goes into structure, then it goes into thermodynamics, then it goes into equilibrium. So we're bouncing around. We got unit 2, then we're back to unit 1, then we're to unit 6, then we're going to do a lot from unit 4 in equilibrium. So there's a lot going on here. And that's another thing to understand, that this course is cumulative, and these are the questions you got to get used to. When we take our unit 2 test, the majority of questions are going to be unit 2 questions, but there'll be some stuff from unit 1. And by the time we get to unit 7, the majority of the questions on that test will be from unit 7, but there'll be stuff from unit 6, unit 5, because you have to understand how everything ties together. And if you know this from something that you learned in unit 4, now you can explain this in unit 6. Okay, so Let's just understand. All right, whoops. All right. So they give us this equation, they give us the delta H for the reaction. We could use that delta H value in stoichiometry. So I'm just kind of, at a glance, when I look at this question, I go, oh, maybe the first question is going to be stoichiometry with delta H. But it doesn't. It just says, so it gives us the description of the reaction that's going on. And then part A is just asking, are hydrogen atoms oxidized or are they reduced in the forward reaction? Justify your answer in terms of oxidation numbers. Okay, so this one, we have a redox reaction. Okay, a lot of times they'll ask you, is it a redox reaction or is it non-redox? This one, they're telling you it's got to be oxidation reduction because hydrogen is either oxidized or reduced, and you have to figure out which one it is. Okay, and it says justify your answers in terms of oxidation numbers. So this is all coming from, if you go to your visible learning document, it's 2-5. It's kind of a hodgepodge of 2-5. It's 1, 3, and 4. So let's look at the visible learning document. 2-5 is just oxidation reduction. And if you look at 1, it says I can assign oxidation numbers. And if you look at number 3, I know the definition of oxidation reduction. And then if you look at number 4, I can identify what's being reduced, what's being oxidized. So we have to identify, is hydrogen being oxidized or is hydrogen being reduced in this reaction? And so let's go to the key. And so the answer is reduced. I assign the oxidation states up here. In this compound, hydrogen has a +1, but as an element, hydrogen has a 0. So it's going from +1 to 0. And if your number, your oxidation state, your oxidation number goes down, that's reduction. If it goes up, that's oxidation. So carbon is going from, well, we'll talk about that later. I don't want to get into all that. But so we're going from +1 in this compound to 0. So it's being reduced. And so you have to explain that. This is an H, my handwriting's not that good. But in this compound, in the methanol, hydrogen is +1, and in H2, hydrogen is 0. And that's what reduction is, okay? So that's part A. I'm thinking this could be worth 2 points. It might be worth 1 point, but saying it's reduced versus oxidized might give you a point, and then identifying the correct oxidation numbers in each thing in the reaction as it goes from reactants to products might be worth another point. Okay, so let's go to 2B. In the following box, draw the complete Lewis dot structure diagram for carbon monoxide molecule in which every atom obeys the octet rule. Show all bonding and non-bonding electrons. So non-bonding electrons are just the lone pairs, okay? So if you go to, so 2B is 1-4. So this is back in unit 1. So, you know, when we start out in AP chemistry, unit 1, we're going to get to a lot of stuff. Unit 1 is a big unit, and it starts in 1-4, we're doing dot structures. Okay, so carbon monoxides, a covalent compound, so you got to be able to draw its dot structure. Don't worry, we'll be doing a ton of this stuff. And carbon monoxide is one that I use for an example a lot over and over again in class. So if you're paying attention in class and you have a good memory, this should have been easy for a lot of my students because, again, I do use carbon monoxide as a big example. So carbon monoxide, it has a triple bond, and it's one of the rare times where carbon actually has a lone pair on it. So notice that this carbon has 2, 4, 6, 8, and the octet rule for carbon is it has to have 8, and the octet rule for oxygen is it also has to have 8. So if you look at the structure, they both have 8 valence electrons. We got a triple bond there, and we're good to go. All right, but you needed the lone pairs. So yeah, it's good to know that carbon monoxide has a triple bond. Sometimes that comes up in other types of questions, that kind of thing. No, because it's a pretty strong bond. But not drawing the lone pair here and the lone pair here would you wouldn't have gotten the point. And yeah, it's probably good to draw the lone pair on the 180 degrees away from the triple bond because the electrons want to be spread out as far as they can, and the symbol represents the nucleus. And so if you're thinking, I know it's really 360 degrees around the nucleus because you got to think 3 dimensions. Or sorry, you can think of, in 3 dimensions, but in a 2-dimensional thing, you got 360 degrees. And so what's the furthest away they can be is 180. So, but if you drew the lone pair on the top here and on the top here, they wouldn't take off for that. That would be fine. All right, so let's look at 2C. So they give us entropy values. So this symbol S is entropy. Any entropy question is going to be unit 6. I'll show you that in a second. So if we look at the question, it's asking to use these standard enthalpy values. So notice that they give us this value called entropy, which, don't worry, we're going to cover plenty in this year. But notice that you have a value for each thing involved in this reaction, okay? So they're saying in part 1, use the data in the table to calculate the delta S for the reaction. So notice this reaction has a delta H value. There's also something called a delta S value. There's also something called a delta G value. There's also an equilibrium constant, which we'll get to in a little bit here. So there's all these different things. And this one's pretty easy. This is just plug and chug into the equation. And so this equation is on your formula sheet. So it says the delta S, and I write this pretty fast, but it's delta S of the reaction equals the sum of the entropies of the products minus the sum of the entropies of the reactants. But notice that this is entropy, so it's energy per temperature and then also per mole. Okay, and so we got to remember that if we have any coefficients in this balanced equation, the coefficients are our mole ratios. So 1 mole of this will yield 1 mole of that, but 2 moles of this. So for the hydrogen value, we have to multiply its entropy value by 2 because of the coefficient 2 here, okay? So all we're doing is plugging into that equation. So remember, it's products minus reactants. Remember, and think of delta, right? Delta means change in something. Change in something is always final minus initial. So if you're talking about the change in a reaction, the final part of a reaction is the products. The initial part of the reaction is the reactants. So when we do delta of a reaction, delta anything, delta S, delta H, delta G, change in anything for a reaction, it's products minus reactants. So our 2 products are these, but notice that for the hydrogen, I doubled it because of the coefficient 2 in front of the hydrogen. So I add up all of those on the product side and then subtract the reactant side, and I get my delta G, or sorry, in this case, my delta S. And notice I didn't include the units when I was just plugging and chugging, but the units are still the same units that they gave us here. So make sure you're including units whenever you do a calculation, okay? So it's the same units from what's in the table. All right, so we get a positive delta S. Now, let me talk about the visible learning. So this is part CI. So CI is 6-1-4. So let's go to the visible learning document and let's go to unit 6. Okay, let's scroll all the way down here to unit 6. And it was 6-1-4. And look at that. I understand how to use standard molar entropies to calculate the delta S for a given reaction. I mean, that's exactly what the question's asking. So again, the visible learning document has all the objectives you need to meet, and here's proof. Boom, you got it. It's right there. Okay. Let's go to the next question. Okay. So the next one, part 2 here, calculate the value of delta G in kilojoules per mole. So here's something to watch out for, right? They want the delta G in kilojoules. You just found the delta S in joules. And if you scroll all the way up, remember, this is all question 2. So the stuff we started with in question 2 still pertains to all this stuff going down. So you'd have to, you might get to this point, you're on the second page of the test, and you're like, how am I going to calculate the delta G? All I have is the delta S because that's fresh in your mind. Remember, they gave you the delta H. They gave you the delta H. You just got to remember that they gave it to you, and now I'm finally going to use that. So for the first few parts of this question, I didn't care about this at all. They didn't ask me any question about the delta H value or where I needed to know about the delta H value. Now all of a sudden I get to part C, part 2, and now I need to remember that I do have this delta H value, right? So let's scroll down here. So there's an equation, and let's go to the visible learning. And this equation's on your formula sheet, so it's not something you have to memorize. You just have to know how to use it. So 6-1-2, so unit 6, 1, 2, I understand how to use the following equation. There you go. So you have the delta H value, you have the delta S value. We'll go back to the test because you also have the temperature value. And so really it's just plugging in and solving for delta G. But like I said before, the delta H was kilojoules and the delta S was joules. So before we plug in, we got to convert the delta S to kilojoules because remember the test asked for delta G in kilojoules. If it didn't ask for delta G in kilojoules, you could do kilojoules or joules, whatever one you wanted, but you'd have to make sure the units agree. So you could take your delta H and convert it from kilojoules to joules and keep your delta S in joules and then get your delta G in joules, but this time they wanted kilojoules, all right? So let's go back to the test. So remember, the delta H was 90 kilojoules. They gave us the temperature, 375 Kelvin, so that's the T. And then we calculated the delta S, 220 joules, but that would be 0.22 kilojoules. So that's why it's 0.22, not 222. So that's what I have to plug in for delta S. So I get my delta G, and it's positive 7.5 kilojoules per mole. Okay. So let's move on to part D. Okay, so part D, they give us a representation of the mixture at equilibrium. So the reaction in question, so it's still, we're talking about this equation, has reached equilibrium. And these are the particles in here, okay? So notice we got 1, 2, 3, 4, 5, 6 hydrogens. We got 1, 2, 3 COs, and we got 1 methanol. And they're all in the gas state, okay? And it says, use information from the particle diagram to calculate the partial pressure of CO, carbon monoxide, at equilibrium when the total pressure in the equilibrium mixture is 12 atmospheres. So inside this container, we have 12 atmospheres. That's the total pressure. And we have to use the particle diagram to calculate the partial pressure, so the pressure just due to the carbon monoxide. So we should be able to do it. We got to count the total particles. So I done it right here, but let's count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Got 10 particles, all right? And 3 of the 10 particles is carbon monoxide. So that means 3/10 of the total pressure would belong to carbon monoxide. So this is Dalton's law of partial pressure using mole fraction, but let's find it on the VLO. So this is part D of the test. So 3-2-6E, 3-2. So now we're back to unit 3. So notice we started off with unit 2, then we went back to unit 1, then we went to unit 6 for a couple questions. Now we're back to unit 3. So let's go find that 3-2-6E. So let's scroll up here. Three dash 2-6E, Dalton's law, partial pressures, mole fraction, collecting energy. So this is the mole fraction one. Remember, mole fraction is the same as particle fraction. So we'll go to the test. So all you have to do is mole fraction times the total pressure. So 3/10, 3 particles were carbon monoxide and a total of 10 particles. So 3/10 times 12, we get the partial pressure of carbon monoxide is 3.6 atmospheres. So that means if they wanted the partial pressure for the methanol, you would just do 1/10 times 12. And if they wanted the partial pressure for hydrogen, you could do 1, 2, 3, 4, 5, 6, 6/10 times 12. Okay. All right. So we go to part E. It says write the equilibrium expression constant Kp for the reaction. So remember, the reaction is still way back up here. So we'll learn about writing equilibrium expressions and all that, but let's look at the VLO. So this is 2E. So it's 4-1 6D, but it's also 4-1 8. And it's because this has to do with it's a specific equilibrium expression. It's a Kp, which is different than all the other equilibrium constants. So let's go 4-1. So if you look at this, 4-1 6, I can write the following equilibrium constant expressions, and notice 6D is the Kp expression, so that's that one. But then it says here, number 8, I understand that the equilibrium constant expression Kp is written with respect to partial pressure. Okay, so to write an equilibrium expression, we do products over reactants. The coefficients become exponents. So products over reactants, and the coefficients, and this has a 2, becomes its exponent, and that's it. So if I want to write the expression, I would say Kp equals, here are my two products, and this is partial pressure notation. So P subscript CO means the partial pressure of CO times the partial pressure of hydrogen squared. Notice that it's P subscript H2 squared, and that 2 came from the coefficient of hydrogen in the equation, divided by the reactant, and there was only one reactant. And both of these guys, the CO and the methanol, both had coefficients of 1, so that's why you don't have to write the exponent 1 here. It's understood. So that would be the expression. Boom, we got it. All right. So here, the reaction system represented, okay. So the following table gives you partial pressures of each species in the equilibrium mixture. So remember, and so this one they said they're studying at a different temperature. So the equilibrium constant is only constant as long as temperature remains constant. So at a different temperature, there's going to be a different Kp value. So at this temperature, it's still the same expression. Kp is still the same expression. But to solve for, if we go to part F, use the information from the table to calculate the value of the equilibrium constant Kp at the new temperature. So they told us these were the equilibrium partial pressures. So this is real easy. All we have to do is plug these numbers into that expression and solve for Kp. So 4.2 is the partial pressure of CO, 8.4 squared for the hydrogen, and then divided by 2.7. Okay, so this would be, I forgot, this is about the visible learning document, so let's go back. So this is part F. So 4-2, 2A. So let's find that on our visible learning document, 4-2 and 2A. I can calculate the equilibrium constant given all equilibrium partial pressures. Okay, that's what I was given all the equilibrium partial pressures. I've already established that I know what the expression is, so all I have to do is plug those into the expression to solve for Kp. So Kp equals 110. Just a quick note, the one thing that you don't, the one calculation you don't need units for is a equilibrium constant calculation. Whenever you calculate an equilibrium constant, you don't need to include units. But what would they be? So you have atmospheres times atmospheres squared. So you have atmospheres cubed divided by atmospheres. So this would end up being atmosphere squared. So if you needed units here, the units would be atmosphere squared. But usually for equilibrium constants, you don't need units because they would be different depending on the expression, depending on the reaction. Okay. The important thing is the value. So the value is telling you that at whatever temperature this reaction is happening, the forward reaction is favored over the reverse because you have more products than reactants. And you know you have more products because equilibrium constant is a ratio of products over reactants. And if that ratio is greater than 1, then your numerator is greater than your denominator. So more products, less reactants, that kind of thing. Okay. All right. So let's go to part G, the last one of this question. So the volume of the container is rapidly doubled with no change in temperature. So we increase the volume. As the equilibrium is reestablished, does the number of moles of CH3OH increase, decrease, or remain the same? Justify your answers by comparing the value of the reaction quotient Q with the value of the equilibrium constant Kp. So if they didn't give us this at the end, if it just said justify your answer, there's actually a couple different ways to justify that the moles of methanol will decrease. But we have to use the Q calculation, not the not the Le Chatelier's principle. But I want to show you kind of both. So if we go to it, so this would be the Q calculation one, 4-28. But 4-3 2CI would be Le Chatelier's principle. So it might be a good idea to know the Le Chatelier's principle one, because you could quickly decide what's supposed to be true using Le Chatelier's principle, and then you'd have to go back and figure out, well, how do I justify it with a Q calculation? So if we go to the visible learning document, so if we go to the 4-3 Le Chatelier's principle, it was 2CI. So I can determine which way the reaction will shift when the following stresses are placed on the reaction system, and we're talking about changing the pressure by increasing or decreasing the volume. Okay. I don't know why I have it there twice like that. That's very redundant, but whatever. All right, anyway. So if we look at the reaction, again, this is one where you're going to go all the way back up, because this is the reaction in him. So for Le Chatelier's principle, let's understand what we did. We increased the volume. So increasing the volume decreases the pressure. So what Le Chatelier's principle tells you is whatever stress you place on a system at equilibrium, if you stress it, so you have a system that's at equilibrium, you stress it somehow, you add something, you take away something, whatever, the reaction is going to try to undo what you did. So if I increase if I increase the volume, that means I've decreased the pressure. If I decrease the pressure, the reaction is going to try to bring the pressure back up. And the only way a reaction can bring the pressure back up is by shifting to the side where there's more gas particles, because more gas particles would mean higher pressure. So if we look at this, the reaction, as the reaction proceeds, we have one gas particle turning into three gas particles, 1 + 2 here. So as the reaction proceeds to the right, the pressure should go up, right? So we're at equilibrium, the pressure is holding constant, then all of a sudden we double the volume. That halves the pressure, right? The pressure cuts in half. And so we know the reaction to reestablish equilibrium is going to shift this way. It's going to shift to the side with more moles of gas. So as it shifts this way, it's going to consume this. So the amount of methanol is going to decrease as it's reestablishing equilibrium. So we know the answer to this last question here in part 2 is moles of the methanol will decrease. But we can't use the Le Chatelier's principles to justify it. Like I could justify it in words, the kind of the way I was just explaining it, but we have to do a Q calculation. So the Q calculation is, if we go back to the visible learning, 4-28. So I want to show you where that is. 4-28. I can make Q calculations to determine which way the reaction needs to proceed to reach equilibrium. And it's telling you if Q is greater than K, it shifts to the left. If Q is less than K, it's going to shift to the right. So we know it's shifting right. So Q has to be less than K, but let's understand how to do a Q calculation. So Q calculation is you plug in the pressures or the concentrations, in this case the pressures, into the same expression that the Kp is equal to. So Qp and Kp are equal to this expression. So when you plug in the equilibrium amounts, then you get a K value. But if you plug in different amounts, then you get a Q value. And then the Q value tells you, and you compare the Q to the K value and see which way it's going to shift. So remember, let's understand what we did here. We doubled the volume. That cuts all the pressures in half. So here are the pressures at equilibrium. If all of a sudden we double it, then this is going to be half, this is going to be half, and this is going to be half. So what we're going to do is plug in those values that are all halved into the same expression that we did up here, and we're going to get a value. So when I half all of those values and I plug them in, I get Q is equal to 27.4. Okay, well, K is equal to 110. So what is that? Q is less than K. When Q is less than K, that's a sign that you have too many reactants and not enough products. So the reaction has to shift towards the products. That means shift to the right to reestablish equilibrium. And as it reestablishes equilibrium, as it shifts to the right, it's consuming CH3OH, the methanol. It's consuming that. So the amount of methanol will go down. Okay? So I'm guessing this one was the other 2-pointer in that question. All right? Okay, so we'll stop there. So far we've gotten through 2 questions. We got a third longer question. So question 3, as we look a little bit further ahead, question 3 is another long question. So question 3 is also worth 10 points. But when we get to questions 4, 5, 6, and 7, they will be shorter. Okay, so hopefully we'll have, I'll do another video tomorrow on question 3, and then hopefully we can do questions like 4 and 5 together, 6 and 7 together, and finish this up in a few videos. But I also, at the end, I want to tally up all the different visible learning objectives you needed to know from our visible learning document, and kind of show you which units were more heavily asked on the free response. And that's the other thing to understand. If a lot of stuff from different units is covered, so if there's a lot of unit 1 or maybe a lot of unit 5 on the free response, then that means there might not have been much of it on the multiple choice. Or if we're finding that there's not a lot of unit 7, because we haven't had any unit 7 questions yet. On questions 1 and 2, we haven't had any unit 7 questions yet. And that might be, if there were not that many unit 7 questions on the free response, that might mean there were a lot of unit 7 questions from the multiple choice. Okay, so anyway, that's it for today's video. I hope you're enjoying your summer.